Thank you, Anna, and thank you, Regis. So to get the ISFOG conference here in France, and particularly in Nantes today, was a fantastic opportunity to discuss about the 6th first offshore wind project in France. We cannot say that in France we've been pioneer in offshore wind. We've been quite late compared to countries like UK, Denmark, and Germany. We awarded the first 4 projects, Saint-Nazaire, Fécamp, Courseulles, and Sant-Brieuc, only in 2012. And the two other projects, Noirmoutier and Treport, 2 years after. And it has been also a long journey before to get the first foundation in the ground. So the first monopile was installed in Saint-Nazaire in 2021. What is remarkable on this 6 projects that you can see on the slide is that they all involve rocky formation. As you can see, the geology on the French coast is quite variable and complex. If I look at the 2 bottom projects, Saint-Nazaire and Noirmoutier, they are both situated on calcarenite bank, the Bande Guérande for Saint-Nazaire and the Plateau des Bœufs for Noirmoutier. So you can find calcarenite and dolomite. But this ground condition offers also some other difficulty, like the very rough seabed condition that you can imagine when looking at the first picture. And the bottom one, you can get an idea of the quality of the rock that you can find. So this is the Chateau of Chantilly that is situated very close to the onshore pile test used for the Saint-Nazaire project. So 2 similar ground conditions, and both projects adopted the same solution, meaning drill and coated monopile with almost the same installation methods. If I now look at the 2 upper sites, Fécamp and Treport, they also offer some similar ground conditions, involving chalk with flint, more or less flint, depending on the layers and project, and limestone. But in that case, 2 different solutions were adopted. For Le Treport, it's more a classical methodology, I would say, with jackets with driven pile, whereas Fécamp opted for a gravity-based structure. For the 2 remaining sites, the geology is very alike, very different, but both involve very heterogeneous ground conditions, and they both considered very different solutions. For Saint-Brieuc, it's jacket with drill and coated piles. And for Courseulles, I will come back to that, but it's a very innovative way to install some monopile. So I didn't work on the 6 projects, but only 3 of them, Fécamp, Courseulles, and Saint-Nazaire. I need to thank a lot Iberdrola and RES for providing me a lot of valuable information on Saint-Brieuc. Before to start with the Saint-Brieuc project, I wanted to recall that the French Committee of Soil Mechanics started to work in 2013 on some guidelines for recommendation for planning and designing foundation of offshore wind turbine. It's mainly based on well-recognized standard and recommendation, but it also includes some specificities for the French challenges, I would say, like recommendation for pile capacity in calcareous soils, dedicated section on both pile, return of experience from onshore French projects and French research projects such as SOCIP, and also an appendix on annular gravity-based foundation. The type of foundation that were used was a met mast on Fécamp. So the site geology of Saint-Brieuc is dominated by Neoproterozoic and Lower Palaeozoic rock of the Cadomian. So the sediments were deposited and subsequently heterogeneously deformed by convergent tectonism and metamorphosed. I heard recently that on the American belt, there was a long time ago a mountain that was up to 7,000 meters, so even greater than the biggest one in the Alps right now. I'm not going to detail all the different geological units. As you can see on this table, you have different type of mineralogy, strengths, or weathering of the state of the rock. But just to highlight that some layers were deliberately avoided for the layout due to their very heterogeneous ground condition and uncertainty in the foundation design. So prior to the design of the foundation, the Saint-Brieuc project ran some onshore pile tests in the northern Brittany, involving 14 drill and coated piles. You can see the pile there with the shear keys. It was obviously not possible to test all the type of geology on the Saint-Brieuc, so the tests were done on the feldspathic sandstone with an average UCS of 90 MPa. You can see on the right the main outcome of this pile test. So the unit shaft resistance is a function of the rock mass stiffness, rock socket roughness, and is inversely proportional to the rock socket diameter. They found also, as you can see on the middle graph, a good consistency with Seidel and Collingwood based on constrained dilatation at rock interface. We can note that for a weak calcareous rock that we found in other projects, the failure occurred in the weak rock rather than at the interface. That is also consistent with some tests that were done for the Sol-Cyprus project. Another outcome of this test is the higher susceptibility to cyclic degradation than for a driven pile in sand. It's what you can see on the stability envelopes on the bottom right figure. So the Saint-Brieuc gets a 3-leg jacket with a 25-meter width between the piles. The hole diameter was almost 3 meters, and the pile diameter 2.8 meters. In terms of installation, the pre-piling used the templates that you can see at the middle. That is quite an advanced one, with some oscillators that allowed the temporary casing to be installed down to the target depth and also to be retrieved at the end of the grouting. What is remarkable on this project is the use of a drilling tool, but not only one at a time, but with simultaneous drilling over the 3 piles. It's what you see on the bottom. You see the 3 drilling tools there. And there you see one type of drilling bit that were used, but several was used in order to improve the duration of the drilling. So Saint-Brieuc is not the only project that involved jackets. There was also the Le Treport project that involved driven piles in chalk, but there was also a jacket for the foundation of the offshore substation. For the Saint-Nazaire Fécamp Courseulles offshore substation, the same drilling tool and almost the same template were considered. However, it's remarkable to see that the installation methodology were very different from one project to another. For Saint-Nazaire, we had drilled and grouted piles. For Fécamp, due to layers that were stronger with some numerous flints, at 13 meters, the pile were driven down to the steps. Then there was a drilling to the target depth and an unset pile when they grouted. And for Courseulles, it was a DDD operation, drive-to-drive, but not with drilling as contingency compared to Le Treport. It was used as a primary installation mean, with a drilling diameter of 80% of the inner diameter. This percentage was selected to compensate or to find the good balance between the risk during driving, but not to decrease too much the external capacity. So now, if we speak about monopile, we heard this morning that usually you don't use monopile if you cannot drive, but in that case, we use monopile when there is rock. So for the Saint-Nazaire project, it's situated on the Lutétian-Barthonian dolomitic calcarenite bank, and below that you have some Ypres sand and clay. But if you see the sketches of the geology there, you have 3, big stratigraphy. You have the calcarenite bank, so with more or less dolomitization. Then after, you have an intermediate layers that is basically the degradation of the upper calcarenite bank. So you have some weak rock interbedded with the sand layers, and then below you have the Ypres and sand and clay. Here you can see an example of ultra-high resolution seismic line obtained with the Ergen source, and the map that were obtained from the structural model. This map provides the thickness of the calcarenite. As you can see, you don't have calcarenite everywhere. You have 6 locations there where you don't have any rock because of the paleochannels that is passing through, and you have one or so there that is due to a depression. And you can also note that on the northeast part, you have a very thin thickness of the calcarenite bank. But please keep in mind, it's not because you have a very nice map that you have a good accuracy. So in that case, the accuracy of the structural model was not sufficient for the project. There are difficulties to infer the accurate thickness of the rock due to the attenuation of the acoustic signal when penetrating the rock, the seismic signal dispersion when the rock interface is irregular, and if you remember the first picture I showed you that represents the seabed condition, it's very irregular, lack of seismic contrast between intact rock and weathered rock, and of course the seabed multiples doesn't help. So for this site, we had to do a borrow per wind turbine location. We could not rely on the structural model. And maybe you will ask, what is the accuracy required for a structural model, particularly for the determination of the thickness of the rock? It's really related to the type of design and installation that you do. And in the present case, what was important is really to get the first significant layer of sand. Because obviously, when you drill, you don't want to drill sand. You don't want to create a cavity that you will need to fill with grout later on. So as for the Sant-Brieuc project, we did run some onshore pile tests for the Saint-Nazaire project. So I won't detail those tests because they were presented already in the last ISFOG. But keep in mind that at this stage of the project, we didn't know yet what was the installation methodology. So we looked at driving, drive, and drill and grouted installation type. And the main observation during this pile test was the gap behind the pile that does not recover with time, the crushing of the material that is very like what you can obtain when you drive pile in chalk, and the cracks that developed during the driving, the blue lines, and that developed during the lateral loading, the red one. So during the start of this onshore pile test, we didn't know which model will suit the best the results. When we did those tests, it was about the moment where PISA developed its concept. There was already, for mainly oil and gas project, some past PY curves in rock, so either with a ductile failure type or with a brittle failure like APS. And there was also all the work done in Australia by Sant-Brieuc with a shipper model that represents really the shipping mechanism during the loading of the pile. So here is a graph from an article written by Mark Randolph in 2019, comparing the results, one of the results of this field test with two models, the RIS one and Airbrich one. To be noted that the initial stiffness were adapted in that case. And I like the conclusion from Mark. It is perhaps somewhat comforting to find that the lateral responses estimating using the very different RIS and Airbrich approaches can lead to relatively similar outcomes. It's maybe a bit frustrating to think that we use some simplified model to represent this very complex mechanism. But the thing is, for this project, we did use some PY curves only, adapted, calibrated to the onshore pile test, but it does the work. In terms of installation, so you saw there was some location without rock, so we just driven them. When there was more than 22 meters about of rock, then we adopted a rock socket installation type. And when the thickness was not sufficient, then it was what we call an hybrid monopile, with drilling through the calcarenite bank, then driving through the transition and the present sand, and then grouting on the annulus. I should say there is even a fourth type of methodology. When the rock was less than 10 meters, then the grouting was not performed. It was considered that it was better to not wait for the curing of the grout rather than to get a smaller pile. On the right-hand side, you can see the pictures from the installation. I won't develop it too much because there will be a presentation from Deme later this afternoon, but you can see the drilling machine, the vertical boring machine, the modiga that is used to prevent the waves to impact too much, but also to lower down the drilling machine. And you can see the 4,000 kilojoule hammer. What is maybe interesting is to get the first return of experience for one of the hybrid location. So you can see there some frequency measured compared to the digital wind for the with or without corrosion. So, at the very early stage of the project, it's better to look at the without corrosion number. So you can see that for the first mode, so the mode that is represented at the middle, we get a delta between the measurement and the prediction of 1.4% only. For the second mode, it's a bit more. We get 13.5%. But considering that the displacement involved in the second mode are much smaller, then it's considered to be quite reasonable if it's less than 20%. Now, another project involving monopile, and you might wonder why I'm starting by that, but we are 4 days after the 81st anniversary of the D-Day. And I just wanted to recall that Courseulles is just in front of Juno Beach, where the Canadian troops arrived. As a direct consequence, you can imagine that we found some, related objects, I would say, in the ground with wrecks, with pontoon bridges. And the thing is, at the Courseulles project, if you look at the brown part, you have some paleochannels that are infilled with very soft sediments. And there was a risk that UXO that we could not detect would be buried in those paleochannels. So the layout considered the avoidance of these paleochannels. In terms of geological units that we can find, you have some marne for Descoville. So it's basically over-consolidated carbonated clay with some indurated layers, Langhorne limestone, so weak carbonate rock with an average UCS of 10 MPa, some stone of Abassecard, that is an alternance between the marl and weak carbonated rock, and some Ranville limestones that are, again, some calcareous rock with some marl sublayers. I used to compare the geology from Courseulles with millefeuille, that is a French pastry with involving many type of layers. But in that present case, it's even a millefeuille that is inclined, because we have a monocline structure, so we have a dipping of the foundation towards the northeast. So you have the older formations that are close to seabed on the west part, and you have the younger one on the east part. So the thickness of the marl, that is above the purple line, is increasing when you go to the east. So as you can imagine, as you can see, from one location to another, the stratigraphy is very different. But compared to Saint-Nazaire, the stratigraphic model was quite accurate. So we didn't need to perform one borehole per location. So we have 27 locations where we infer the stratigraphy based on the geomodel. So I told you the installation type in Courseulles was quite innovative. So the idea, the concept, is basically to drill a hole that is longer than 1 meter than the monopile, then to install at the same time a casing that will be subsequently grouted, then to fill the hole with sand, then gravels. Gravels are at the upper part, and then to vibrocompact the sand and the gravels, then to verify that the compaction is at the level that you want, and then only with another vessel you will come with your monopile and do the vibro installation. So vibro installation of monopile is becoming more and more common, but as you can see there, it's not in the free field, it's with some constraint. You have the confinement due to the rock and the casing. So there was a lot of uncertainty whether there will be some unknown effects that will make the vibro driving more difficult than in free field condition. So some onshore pile tests were performed with a scale of 1/3 in 3 different density of the granula. And the results showed that it was very easy to drive, vibro drive those piles, and that the stresses recorded by pile driving analysis were very small. So here's some images of the installation. At the moment, only 4 monopiles were installed, but it was a very vibro installation, very easy vibro installation. The drilling is a bit more challenging, let's say. So now, going to a gravity-based structure, the Fécamp project. So as mentioned before, it's mainly involved chalk rocks from Upper Cretaceous. So you have Cenozoic, Turonian, and Cenomanian ages. To be noted that in the Cenozoic, you had a lot of flints. You can see on this geological section that you have a lot of black beds of flint. And it's important because we thought that it was not possible without buckling to drive monopiles. That's the main reason why we went for a gravity-based foundation. Another particularity of Fécamp is that it's crossed by the Fécamp-Libon fault. And you can clearly see the fault there on the stratigraphic model. Of course, we didn't put any turbine right on the fault. And of course, the fault is not active anymore. One of the main challenges of Fécamp was really the characterization of the upper chalk. The first samples we recovered were really damaged. I even heard a contractor that proposed to remove the 8 first meter of chalk before to place the gravity-based foundation. But of course, from an environmental point of view and logistic point of view, it was absolutely not possible. So we had to find a better way to characterize the chalk. And someone came up with the idea to perform vibro core, but with a large diameter one. So you can see on the left an image of the liner that is almost of 500 millimeter. And then after that were trimmed into 300 millimeter. So you can see that the chalk is not homogeneous. It's made of denser blocks in a matrix that is softer and with some flint nodules that you can see there. Then after, those samples were tested in a 300 millimeter triaxial cell. So we did a lot of tests, but what was interesting with the sequence of the cyclic tests you can see there, so between 2 stages you have some drainage. We had an increase of the static resistance post-cyclic. We had dilatant behaviors that were also more pronounced, and the permeability that decreased after the cycles. Unfortunately, we could not take all the benefit of this behavior because you simply don't know when the designing storm is happening. So you need to consider that it could happen just after the installation of the wind turbine. So I won't detail that because for you it's obvious, but when you design a gravity-based structure, you need to look at the bearing capacity, the sliding capacity, overturning. You need also to ensure that there is no erosion due to pumping or flushing below the gravity-based foundation. But it was just to say that depending on the water depth and the ground condition, the driving criteria for the diameter of the slab was the sliding capacity or the no or limited capping criteria. So the main figures of the Fécamp GBS, it's a slab of 31 meter diameter, a score protection of 44.6 diameter, and a weight of almost 5,000 tons. And we had to add also some sand ballast after installation of 2,600 cubic meters. Well, we are only 2 years after the installation, but we already get 25 years return period storm. So we could already see that the settlement and tilt value are within the expectation. And interestingly, that the global tilt that is done, made by the fabrication and installation tolerance plus the settlements has been reoriented in the main wave direction, what makes sense. So some image comparing one of the GBS for the wind turbine and the met masts at the right that were installed much before the wind turbine. And the last slide on Fécamp showing the construction phase. Quite an impressive site with 71 GBS built almost at the same time. You see different stage of the construction. Then the towing to the site and the lifting by an heavy lift vessel. So there are many other aspects that are developed in the papers. I encourage you to read it. There was many geohazards in those sites, like falls, boulder, karstic features, paleo valleys, igneous dike. The importance of the reliability of rock mass determination and also the determination of the whole roughness. It's very important for a drill and grouted structure. And you can see on the top right some images from the Sant-Brieuc project where luckily they've been able to send a video, a camera inside one of the holes to see what was the type of indentation you can get after the drilling. One topic that were of a concern on Saint-Nazaire was the jacking on the very uneven rock. So jacking on outcropping rock can involve either seabed preparation, spud can modification, like you can see on this sketch, but also implementing dumping system on the jackup itself. To install cables on outcropping rock is also quite a challenge. We did some tests at Fécamp, Courseulles, and Saint-Nazaire quite early in the development phase. So the rock in Saint-Nazaire, it was able to be drilled. It was not so much the issue. It was just the machine that could not go, could not stay in line due to the uneven seabed. So we had to consider some protection for the cables with cast iron shell. And you can see there the image where the marine life is already taking its place. So, as conclusion, it's quite remarkable that over the six first projects in France, they all involve rock, as I said, but they also consider 5 very different approaches for the foundation. You probably understood that rocky formation came with many challenges. The difficulty to map the bottom of the rock unit. We had to consider advanced and innovative solutions to recover and to log the weak rock material. We also had to consider custom-made installation concepts and tools for those projects. Hopefully, the development phase were quite long and allowed all this work to be done. And one thing that is very particular, when we speak about drilling, most of the time it's about contingency. But in this particular case, drilling was not as contingency apart for the Le Treport project. Kilometers of drilling were involved. So it was very important to get reliable ground condition, realistic all collapse analyses, because you don't want some temporary or permanent casings that are too long. And you need specific drilling tools. And again, hopefully, we get a long development time that allows that. On the positive side, many other projects are to come, either in France or in Japan or other seas, that will involve a very complex rocky conditions. So it's many interesting work for most of us in this room that are coming in the coming years, either for fixed bottom or floating foundation. So I'd like to thank all the engineers in this room that worked on these 6 projects, and I think that you are quite numerous, either from a developer, from contractor, consultant, or even certification body side. Thank you very much that you made a success of this project. So I cannot name everyone, but I'd like to name 2 people that made a significant impact on most of this project. The first one, you met him this morning, he was our brigadier, it's Alain Puech. Alain trained over the years several engineers, geological engineers in France, and many people in this room also worked with Alain. Alain spent a tremendous energy to gather the university and the industry in France to pursue some research program like SOCIP. but also the technical group of the French Committee of Soil Mechanics who worked on the guideline for both fixed bottom and floating. The second person is Richard Jardine. Richard made the impossible task to build a bridge between France and UK to ensure that we get some experience from the other side of the channel implemented in all those projects. So thank you, everyone.